graph theory. To begin with, what is a graph? It is a set of vertices and a set of edges. So for this given graph, you can write the set of vertices as u, v, w, and z. Set of edges as u, v, v, w, v, z, and w, z. The kind of graph we are discussing in this session is a simple graph. So in simple graph, you have no loops and no multiple edges. Also, the nature of edge is undirected edge and there is no weight on edge. So we are not discussing directed graph, pseudo graph, multigraph, weighted graph in this session. We are only going to discuss simple graph, which is undirected and unweighted without any loops or multiple edges. Okay, another terminology is regarding adjacency. So if there is an edge between u and v, you say u is adjacent to v, and this relation is symmetric. So we also say v is adjacent to u. So in other words, you can say u and v are adjacent. There are another pair, more pairs like W and Z, they are adjacent. W and V, they are adjacent. Z and W, they are adjacent. In this next second graph, V1, V5, they are adjacent. V1, V2, they are adjacent. V2, V5, they are adjacent. V4, V5, they are adjacent, and so on. The next terminology is neighborhood. So neighbor of a vertex. Suppose you consider the vertex V in the first graph, then what are the neighbors of vertex V? It is a collection of all those vertices which is adjacent to V. So U is adjacent to V, W is adjacent to V, Z is adjacent to V. You can also consider a collection of vertices and then talk about neighbor of those subset. In other words, neighbor of, suppose you take the collection of V2 and V4. Okay, so what is this collection of all vertices which are adjacent to V2 or V2 or both? So what are the vertices adjacent to V2? V1 is adjacent, V3 is adjacent, V5 is adjacent. Next, V4. What are the vertices which are adjacent to V4? V1 is adjacent, already in the group, already in the set. V3 is adjacent, already in the set. V5 is adjacent, already in the set. So this is the neighbor of the subset of vertices. Next terminology, next we will discuss the handshaking lemma. What is handshaking lemma? Handshaking lemma. It is summation of degree of the vertices, where you run the summation over the vertices. This is equal to twice the number of edges, twice the number of edges. What is degree, by the way? For example, degree of vertex u in the first graph, what it is? 1. That means how many edges are attached to u? How many edges? 1 edges. What about degree of v? Degree of v is 3. How many edges are attached to v? 3. In the second graph, what is the degree of v5? Which is equal to the number of edges attached to v5, which is 4, and so on. So we'll verify the handshaking lemma for the first graph. In the first graph, you have degree of u plus degree of v plus degree of w plus degree of z. What is degree of u? 1 plus what is degree of v? 3 plus what is degree of w? 2 plus what is degree of z? 2. This is equal to 8. And how many edges do we have? How many edges do we have in the first graph? E1, E2, E3, E4, 4 edges. So what is the relation between 8 and 4? 8 is equal to 2 times 4. Hence, the handshaking lemma is verified for this graph. You can also verify for the second graph. In the second graph, what is the degree of vertex V1? 3. What is the degree of vertex V2? 3. What is the degree of vertex V3? 3. V4? 3. V5? 4. What is the sum of all the vertices? 16. And you can count the number of edges. It must be 8. 1, 1, 1, 2, 3, 4, 5, 6, 7, 8. So you see the number of edges are 8, and hence the handshaking lemma is verified for the second graph. Next, we discuss path. What is a path? It is a sequence of vertices such that the corresponding consecutive vertices are adjacent. For example, in this case, if we write this sequence V1, V2, V3, V4, V5, then graphically this sequence will represent V1 adjacent to V2, adjacent to V3, adjacent to V4, adjacent to V5, and it is called a path of length 4. Length 4 means number of edges are 4, and we represent it by P5. That means we have considered 5 vertices. We can also draw P4. So this will be like 1, 2, 3, 4. What does this mean? 1 is adjacent to 2, 2 is adjacent to 3, 3 is adjacent to 4. So it is your choice how you label it. I will give one more example with different label. 3, 1, 2, 5, 4. So this is also a path. If it is representing a path, so what will be its pictorial representation? 3 adjacent to 1, adjacent to 2, adjacent to 5, adjacent to 4. Next, cycle. What is a cycle? It is like a path whose end vertices are same. In other words, cycle of length 5 can be represented as V1, V2, V3, V4, V5, and you end it with V1. Graphically, you can represent it as V1 adjacent to V2, adjacent to V3, adjacent to V4, adjacent to V5, adjacent to V1. Similarly, you have a cycle of length 3. This is the smallest cycle. Then you have a cycle of length 4, and so on. Next, tree. What is a tree? A tree is a connected graph, and it has no cycle. What do you mean by connected graph? You pick any two vertices, there exists a path connecting the two, and it has no cycle, means you start from any vertices, you are not going to come back to the same vertex. This is not allowed, and it exists for any pair of vertices. For example, a tree on two vertices. This is a tree. A tree on one vertex. A tree on three vertex. A tree on four vertex. A tree on four vertex. This is also a tree on four vertex. A tree on five vertex. This is a tree on five vertex. Another tree on five vertex. Another tree on five vertex. Next, we can have a tree on six vertices. This is a tree on six vertices. This is also a tree on six vertices, and so on. So you see that you pick any two vertex, there exist, suppose you pick this vertex X and this vertex Y, there exists a path From this vertex, you can move to this vertex, then this vertex, then this vertex. So you see there exists a path connecting the two vertices. So it is a connected graph. Plus there is no cycle. It means you begin from any vertex, you will never come back to the same vertex using a cycle or path. Okay, just a quick reminder. When you're discussing about path in a graph, when you're discussing a path in a graph, then you have to ensure that all the vertices are distinct. For example, suppose you consider this graph, name it as 1, 2, 3, 4, 5, 6, and someone asks you that write a path from 1 to 4. So what will be the path? 1, 2, 3, 4. You see that all the vertices are distinct. Another path from 1 to 4 can be 1, 6, 5, 4. Another path from 1 to 4 can be 1, 2, 5, 4. So you see whatever path you are looking for in a graph, it must contain a sequence of distinct vertices, and that sequence must satisfy the property that consecutive terms are adjacent. Similarly, if you are looking for a cycle in the graph, similarly, for example, you are looking for a cycle that starts with 2. So this is your cycle. These are all paths. Cycles on this graph, you start with 2, you go to 3, then go to 4, then go to 5, then end at 2. Another cycle can be start with 2, go to 1, go to 6, go to 5, and go back to 2. Another cycle can be start with 2, go to 3, go to 4, 5, 6, 1, and 2. So these are all cycles. This cycle is of length 4, this cycle is of length 1, 2, 3, 4, 5, 6. Clear? So in this case also you see all the vertices are distinct except the end one, because they are coming back to the same vertex. Okay. Complete graph. What is a complete graph? In a complete graph, all possible pair of vertices are adjacent. This is a complete graph. We represent it using Kn. When n is equal to 1, then you get a single vertex. When n is equal to 2, n equal to 2 means two vertices. You get two vertices and all pair of vertices are adjacent. K3, you get the three vertices and all pair of vertices are adjacent. So this is your complete graph on three vertices. Similarly, K4, you take four vertices and all pair of vertices are adjacent. Similarly, K5, you take five vertices and you see all pair of vertices are adjacent. You can use handshaking lemma to calculate the number of edges, and you can also use a combination to calculate the number of edges. So if you use the combination, what is the rule for complete graph? That all pair of vertices are adjacent. How many ways you can pick the pair of vertices? N choose 2. If you use handshaking lemma, still you will get the same value. And know that this is also a regular graph. So what is the regularity of Kn? N minus 1. What is the regular graph? The number of attachment, the number of edges associated with every vertex are same. And how many edges are attached with a vertex? N minus 1. And how many such vertices are there? N vertices. So this is a regular graph. This is a three regular graph. What is the degree of every vertex? 1, 2, 3, 3, 3, 3, 3, and 3. So this is a three regular graph. This is also a three regular graph. Bipartite graph. What is a bipartite graph? You have a graph and you are able to partition the vertices into two parts such that in each part no pair of vertices are adjacent, and if adjacency exists, it will exist between the pair of vertices from two different parts. So pictorially it represents like this. For example, suppose you consider this graph. V1, V2. Is it bipartite? Yes, it is bipartite. You can put V1 in part 1, V2 in part 2. This is your V1, this is your V2 in part 2, and this is an edge. What about this graph? V1, V2. For simplicity, I will use the label 1, 2, 3. So put 1 in first part. So 1 is adjacent to 2. So 2 will go in the second part. Where will 3 go? Where will 3 go? It is not possible to put in part 1 because 3 should not be adjacent to 1. Can you put 3 in part 2? No, because 3 is adjacent to 2 as well. So this is not bipartite. This is not bipartite. Let's consider one more example. 1, 2, 3, 4. Is it a bipartite graph? Let's figure out. This is your part 1. This is your part 2. Put vertex 1 without loss of generality in part 1. Where will vertex 2 go? 2 is adjacent to 1, so it will go here. Where will vertex 4 go? 4 it is adjacent to 1, so it cannot belong to part 1, so it must go to part 2. So is 2 and 4 adjacent? No. So both can lie in part 2. What about vertex 3? Vertex 3 is adjacent to 2, so it cannot belong to part 2. Can it go to part 3? Yes, it can go to part 3 because 3 is not adjacent to 1. Now you can draw the edges. So this is your bipartite graph. In general, if you talk about cycle, if it is odd cycle, then it is not bipartite. This is not bipartite. You can try to figure it out by yourself. This is part 1, this is part 2. Vertex 1 will go here, vertex 2 will go here, vertex 3 will go here, vertex 4 will go here. Where will vertex 5 go? It cannot go to part 1 because it is adjacent to 1. It cannot go to part 2 because it is adjacent to 4. So in general, this is odd cycle. It is not bipartite. There is a result given in the slides. You can read those results. Euler and Hamiltonian path. It depends on which book you are studying. So you have to be careful about the terminology used. You have a term path, then you have a term trail. Then you have a term cycle, which is treated as closed path. That means end vertices are same. In trail, in circuit, what is circuit? This is treated as closed trail. So if you remember, what is a path? It is a sequence of distinct vertices such that consecutive vertices are adjacent. What is a trail? It is also a sequence, but in this case, edges are not repeated, but vertices may be repeated. Vertices may be repeated. For clarity, you can study the definition of walk. With respect to walk, you can define trail and path. So in other words, for simplicity, for the purpose of this session, we'll look path as a sequence of vertices. We'll look trail as a sequence of edges such that edges are distinct. Vertices may be distinct or may not be. In path, vertices are distinct. So here, for our simplicity for this session, sequence of vertices, distinct vertices, sequence of distinct vertices such that consecutive vertices are adjacent, and for simplicity, trail is sequence of distinct edges. Vertices may be repeated in this sequence. So in this given graph, can you find Hamiltonian path, Eulerian trail, Hamiltonian cycle, or Eulerian circuit? What is Hamiltonian path? Hamiltonian path is a path which consists all the vertices. What is Eulerian trail? It is a trail which consists all the edges. What is Hamiltonian cycle? It is a cycle which consists all the vertices. What is Eulerian circuit? It is a circuit which consists of all the edges. So let's begin. Looking for Hamiltonian path, you begin with 1. then go here 2, then go here 3, then go here 4, then go here 5. So this is your sequence 1, 2, 3, 5, 4. This is a path, so you have a Hamiltonian path. If you add one more vertex, you will also get Hamiltonian cycle. So this is your Hamiltonian path, and this one is Hamiltonian cycle. Does it also have Eulerian trail? Okay. So you have E1, E2, E3. After E3, where will you go? You can go from 5 to 2, E4. You can go from 5 to 1. You can go from 5 to 4. It is not going to help you. If you remember in the lecture, we have discussed that if you have Eulerian trail, this is only possible when there is only two vertices having odd degree. Rest all the vertices must be even. This is the criteria for the existence of Eulerian trail. So how many vertices you have of degree odd? Vertex 1 degree 3, vertex 2 degree 3, vertex 3 degree 3. So you have 4 vertices having degree 3. So it does not have Eulerian trail, and definitely it does not have Eulerian circuit. For Eulerian circuit, what was the criteria? That all the vertices have even degree, then only Eulerian circuit will exist. Now let's look at the second graph. Does it have Eulerian trail or Eulerian circuit? See, the vertex 1 has degree 4, vertex 2, 3, 4, 5 all have degree 2. Therefore, it does not have Eulerian trail. Eulerian trail means you cannot start from a vertex and end at another vertex covering all the edges. But it has Eulerian circuit. You see, you start from anywhere you wish, doesn't matter. You start from here, V3, go to V2, from V2 go to V1, from V1 go to V4, from V4 go to V5, from V5 go to V1, from V1 go back to V3. So this is your Eulerian circuit. Eulerian circuit. V3, V2, V1, V4, then V5, then V1, then coming back to V3. Similarly, in next graph, in the third graph, can you find Eulerian trail or Eulerian circuit? You have vertex A whose degree is 3. You have vertex B whose degree is 3. And all the other vertices have degree, even degree. E has degree 2, D has degree 4, C has degree 4. So it does not have Eulerian circuit, but it has Eulerian path. So what you will do, you will start from A and end at B, or you start from B and end at A. Let's begin. You start from A to D, D to E, E to C, C to B, B to D, D to C, C to A, and A to B. So all the edges are covered. So you can write it down here. Eulerian trail, A to D, D to E, E to C, C to B, B to D, D to C, C to B, C to A, and A to B. A, D, E, C, B, D, C, A, B. Okay. Next. This is just for the exercise. You can try to figure out whether it has Hamiltonian cycle, circuit, Eulerian trail, or Eulerian circuit. Graph coloring. What is graph coloring? You have to ensure that you use the color such that no adjacent vertices are given same color. For example, if you use this graph, then This one can be colored red, this one can be colored black, and so on. Suppose you consider this graph. So this can be colored using yellow, this can be colored using green, this can be colored using white, and this can be colored using black. So this is the rule you should follow while coloring the vertices. And what is chromatic number? What is chromatic number? Chromatic number is the minimum number of color required to color all the vertices. In this case, chromatic number is, we represent it is by chi. Chromatic number is 2. In this case, chromatic number is 3. Can you color this graph using 2 color? No. Minimum color required to color this graph is 3. Similarly, what about this graph? Chromatic number of this cyclic graph C5, you take it box, circle, box, circle, and then you cannot have, neither have a box, because two box cannot be same. Box I am representing as color and circle I am representing as different color. You can neither have circle here nor box here. So you will require some other color here. So the chromatic number is 3. Similarly, can you find the chromatic number of this graph? So let me label the color as 1, 2, 3, 4 instead of the actual color. So color 1, color 2, this I can give color 1, this I can give color 3, because I can neither assign it 1 nor assign it as 2. This I can give color as 1, this I can give color as 3. So what is the chromatic number? The chromatic number is 3 for this graph, because 3 is the minimum number of color required. You cannot color it using 2 color. Next, we discuss graph representation. We'll only discuss adjacency matrix and incidence matrix. Incidence matrix. So what is adjacency matrix? It is a n by n matrix such that the entries at I comma j position is equal to 1 if I and j are adjacent, otherwise it is 0. Otherwise it is 0. For example, consider this graph. Consider this graph 1, 2, 3, 4. What you need to do? You need to form a matrix, label the rows and columns in the same order with respect to vertices 1, 2, 3, 4. You also label the column in the same order 1, 2, 3, 4. Now, if 1 and 1 is connected, put 1, otherwise 0. So in this graph, 1 is, we do not have loop, so definitely 1 and 1, it is not adjacent. 1 is adjacent to 2, 1 is adjacent to 4, 1 is not adjacent to 3. Similarly, 2 is adjacent to 1, 2 is not adjacent to 2, because we do not have loop here. 2 is adjacent to 3, and 2 is not adjacent to 4. Similarly, 3 is adjacent to, not adjacent to 1, adjacent to 2, not adjacent to 3, but adjacent to 4. Similarly, 4 adjacent to 1, not with 2, adjacent to 3, not with 4 itself. If you see it clearly, adjacency matrix is a symmetric matrix and it has several properties. We are not going to discuss all those. Incidence matrix. For the same graph, what will be the incidence matrix? You have to label the rows with respect to vertices, and you have to label the columns with respect to edges. So first name the edges. This is edge number 1, this is edge number 2, this is edge number 4, this is edge number 3, E1, E2, E3, E4. So it depends on the how you label the edges and vertices. Accordingly, your incidence matrix will be formed. So 1 is incident on E1, yes, put it 1. 1 is incident on E4, yes, put it 1. Remaining it will be 0. 2 is incident on E1, yes. 2 is incident on E2, yes. Remaining will be 0. This one will be 0. This one will be 0. 3 incident on E2, yes. This one will be 0. So you can go column wise. You can look at E3. What E3 is incident on 3 and 4. 3 and 4. What E4 is incident on 1 and 4. 1 and 4. So you see that in every column you only have two non-zero entry. Rest all the entries will be 0, which is very clear from the geometrical representation, because every edge has exactly two vertices on which it is incident on. So therefore every column has only two entries. You can answer few of the basic questions. For example, what is the degree of 2? Using the adjacency matrix, look at the row 2, add all the non-zero entries, you will get 2. So the degree is 2. Degree of 2 is 2. You look at the incidence matrix. Can you find the degree of 2? Yes, you can find the degree of 2. What is the degree of 2? How many edges are adjacent with 2? E1 is adjacent, E2 is adjacent, hence 2. So both graph is able to give you the questions regarding the degree of vertices.